All right, so I still have 2 more minutes. I was trying to fix a problem with an erroneous syntax highlighting in Vim, where it it marks something as wrong when it's not. So that's one thing that I was trying to fix. Yeah, I see. I do that to my actual face-to-face lectures too. I'm usually a little bit early, just a little. All right. So I'm just looking at the time. I hope you guys got some time to kind of look at the questions in the questions channel. Some of those are kind of interesting. Like the congruent modulo and notation. I hope you guys were exposed to that at some point in time in high school. If not, it's okay. I can that's pretty easy to explain. Alrighty. Well, when I was teaching face to face, I actually got a class with only 3 students, and it was exactly like that. It's like 3 mannequins in the classroom, kind of half smiling, having that kind of, I was about to say creepy, but I would replace that word with interesting Mona Lisa kind of smile. Yeah, I got 3 people exactly doing that, and they're all related. Yep. So that was interesting. That was interesting. All right, we got about 10 more seconds. I got my coffee. I know some of you commented before, drinking coffee at 5:30. Well, as it turns out, I slept like a baby, without any problems. All right, so it's time to get started. All right, so we are going to get through two's complement, and also we'll talk about comparison just a little bit. Now I know that I already have put binary number comparison over here. This is kind of older. Over time, I explained this topic several times, and I use these notes and go like, that there has to be a better way to explain this, and I did find a better way to explain it. It's just that I you know didn't have enough time to integrate it into here. All right, so I can still go through a part of this. The first part is in section 2. That's actually pretty useful and universal for this class, which is in order to determine or in order to see how two values compare. I really just need to know whether the first one is less than the second one, because everything else I can just use. I can reverse the order of the comparison, or I can use some of the logical operators like or, and so on. So I'm just going to quickly illustrate what I mean by that. So we have x is less than y is exactly the same thing as x is less than y, so that's trivial. If I want to see whether a value is greater than the other value, all I have to do is to exchange the order. Then it becomes a less than. If I want to see if x is less than or equal to y, it is not the case that y is less than x. If I want to see if x is greater than or equal to y, I mean that's exactly the same as the previous one, except the order is exchanged. And then we have x does not equal to y. This one is kind of interesting because it boils down to x is less than y or y is less than x. So so we can still use just less than to see if two values are different or not, because if they're different, one has to be less than the other one. And then finally we have equal to, and I was too lazy to translate it to anything else, so I was just using the negation of the previous one. So as you can see, less than is all you need for comparison, just like NAND is all you need for logical operations. So if I really want to invent a very minimalist programming language, then it has one single comparison operator, which is less than, and one single logical operator, which is NAND. And that will probably make a lot of people it's going to create headaches for a lot of people. Or people just create macros to replace the NAND and less than operations with the fancy stuff like this. They just have to expand the operation a little bit. All right, so I am gonna guess there are no questions at this point. I will pause, just to make sure, that there are no questions at this point. And by the way, we only have, according to YouTube, I only have like 30, maybe 30-ish, like 28, 29 people watching right now, which is kind of interesting. Huh. There are more playbacks than there are concurrent viewers. Anyway. Alright, so we have some people typing right now. Unfortunately, YouTube has this lag time, so things are going to be a little bit interesting. Good time to take attendance. Yes. I'm going to give people a little bit more time, but coming to class late really kind of hurts because then they're going to get into this discussion, not getting the beginning of the discussion, and it's not going to be effective, not going to be as effective as showing up from the beginning. So that's it. Okay, do we have any questions about comparisons? All right, so apparently there are no questions about comparison. So I'm going to move on to unsigned comparison. For those of you who read this note here, this module, you probably will be a little bit confused of about this whole section. The first one is not too bad. Okay, so let's take a look at the first one. I'm not going to go through the proof itself. I'm just going to talk about the conclusion of the proof. So if you have some number n, 2 to the power of n is always greater than the summation of I going from 0 to n minus 1, and each term in the sigma or in the sum is 2 to the power of I. And I'll give you one example really quick. Just say n is 4, okay? 2 to the power of 4 is 16, and it is greater than 1 plus 2 plus 4 plus 8, which adds up to only 15. So if you add up all the lower powers in base 2, they're always going to be, the sum of all of that is always going to be 1 short of 2 to the power of n in this case. And the theorem can be proven using proof by induction, and that's what basically is happening here, is proof by induction. So starting from here, and I think ending up, whoa, okay, ending up here, that is the induction proof of this particular kind of small theorem. I mean, it's not super duper important, but it is a tool that I'm going to use later. So once again, this class is not CISP310, so I'm not going to focus too much on the proof. Now, the reason why I put the proof into the module is twofold. One is I cannot teach something that I personally cannot verify. So since I'm going to verify anyway, I might as well just kind of put it into the module and go like, okay, so if you want to prove it, this is how we do it. So that's one. And then two is I think it is important for everybody to start to realize that a lot of times you cannot just take a theorem and say, yeah, if the professor said that, if Professor Tag says that, then it has to be the case. Nope, no, you really kind of want to be able to independently prove a theorem, and just then you can see for yourself, okay, that the theorem is true. That part gets more important when you get to upper division classes in computer science, and for those of you who want to get into graduate school, that also becomes like really important. All right, so moving right along. So now we want to look at the borrow flag. Okay, so we want to see why the borrow flag, the overall borrow flag, is going to tell us whether the minuend is less than the subtrahend or not. Okay, so it can only tell you whether x is less than y or not. It cannot really tell you whether they're equal or not, or less than or equal to, because we know that those operators can be done using just less than. We just have to kind of combine the comparison operator with some logical operators. All right, so, and now is a good time to, nope, not take row yet. And I am going to put my notes here. This is the notes that I typed just right before the class. Oh, I forgot. Good thing I typed this note, because if I did not, I would probably forget to mention all of this important stuff. Next Thursday, 1 week from today, is going to be our practice exam 1. So next week is week 5. So our actual exam is going to be a little bit late in week 6. Okay, so the time is kind of more or less give or take about half a week or so. So we are going to have exam 1 on the 24th of February. So you might want to mark your calendar right now. It's going to happen during the lecture time of the class. So it will start at 5:30 and it will end at 6:50 p.m. on the 24th. Okay, so you might want to write it down, on your calendar. So that being said, we're going to move on to this conclusion here. After a m-bit subtraction, x is the minuend, y is the subtrahend. Assuming t0 is a 0, which is appropriate most of the time unless we want to use the subtractor to stack, quote-unquote, stack subtractions. In other words, if your subtractor is only capable of, let's just say, 4-bit subtraction, but you have like 16 integers that you want to perform subtraction on, then you can break up the 16-bit into 4 groups, each one having only 4 bits. And in that case, then the overall borrow of one subtraction becomes the t0 of the next one. This is how you can daisy chain subtraction, and then once you have like a 4-bit subtractor, you can actually perform, you can just chain it for as long as you want to. So you can actually use a 4-bit subtractor to perform, let's say, 64-bit subtraction, but it's going to take like 16 iterations to do that, so it's going to take more time. All right, so assuming t0 is a 0, tm, because we have m bits, so this is the one that is not, that's extra, right? This is the one that is hanging on the side, on the left-hand side. So tm is going to be a 1 if and only if, so IFF is if and only if, VU xm is less than VU ym. Alright, so let me explain the notation, because otherwise people just go like, whoa, where are these things coming from? VU is value, and then the U is unsigned. So we are looking at the unsigned value represented by X as a bit pattern, but we're only interpreting up to m digits of X as a binary number. So the question is, why are we only interpreting maybe a part of the entire bit pattern? Well, that becomes useful and apparent in later on. So that's just the notation. If you want to just look at this and kind of say, okay, so this is really just looking at a bit pattern X and trying to figure out what kind of unsigned value is representing. Yeah, I would say that's really a good interpretation of what this is. Except for the m here, that's basically interpreting up to m bits, starting with bit 0. So the last bit that is actually used is going to be m minus 1. Okay. And the definition of VUWM, oh wow, that's a little hard to pronounce. So basically this time, I'm given a bit pattern called W. So the way this is calculated is something that you have seen already. This is from base conversion. So all we do is we look at each digit, from digit 0 up to digit m minus 1, and then each term in the summation is just WI, which is the bit position I of W times 2 to the power of I. So this is nothing new. It's just I'm using this kind of obscure notation so that I can separate the representation, which is just a bunch of bits, from the value the digits are representing. So let me just kind of pause here, because I just introduced a bunch of symbols and whatnot. So I just want to make sure that people have no questions at this time before I continue. And I think the lag time is about 10 seconds. So I can always just kind of wait 10 seconds for that. I think that give has been used before. You guys have to find something fresher. W is just a bit pattern. W is a bunch of bits, at least m of them, but we are only looking at the least significant m bits. So in other words, this, which is which has a definition of this, is really just to say, well, I have a bit pattern called W. It may be 64-bit long, it may be 120-bit wide, but I'm only looking at the least significant m bits of that entire bit pattern, and I want to know what is the unsigned value represented by those m bits. All right, so examples may help, right? So let me just go ahead and see if I can give you an example. And let's see. All right, so I'm just looking on the side here. All right, so I can put one here. Example. Okay. So I'm gonna type in v u. So v is value, u is unsigned. So vu is really just unsigned value. Okay, and we're gonna take a look at 101 1 1 0 1 0. Okay. Maybe another one here. All right, so this is a bit pattern, and we can look at not the entire thing. We can just focus on, let's say, 3 bits of the entire thing. So now, what exactly is that? So you expand it, right? So it becomes the sigma notation. So using the sigma notation, we have 1 times 1 plus 1 times 2 plus 0 times 4. So this entire thing actually has a value of 3. But I'm going to break it up just so that you can see why we're going to end up with a value of 3. So we have 1 of 1. So we have 1 of 1, or 2 to the power of 0, plus 1 of 2 to the power of 1, plus 0 of 2 to the power of 2. And that's it. Okay, so you just add up these things, and that turns out to be 3. Is that okay? Are you guys getting a better idea of what the notation is trying to say? Okay, all right. So that's all it is. It's just a notation of saying, let's just look at a part of a bit pattern, and we want to look at it from the perspective of unsigned representation, and what kind of value is it representing if we just kind of look at these bits. Okay. All right, cool. So now that we have this notation explained, we want to prove what I claimed up here. Okay, so what I claimed up here is so x is a bit pattern. So x is 64-bit, 128-bit, whatever, right? So y has to be of the same width. So x and y are bit patterns of the same width. We make the assumption that t0, which is the borrow that belongs to the least significant column in a multi-digit subtraction, is a 0. So the theorem, or the claim, is this part here. So the claim is basically saying, Tm, which is the overall borrow, up to, if we just look at the least significant m bits, the overall borrow of that subtraction is a 1 if and only if the unsigned value of x is less than the unsigned value of y if we just look at the least significant m bits. That's what the theorem is trying to say. So the question is, okay, so if that is the theorem, how do we prove it? The proof is down here. Okay, cool. So the proof is down here. We have a base case where t1 is a 1 if and only if, so basically I substitute m equals to 1, and in here, the only time t1 is a 1 is when x0 is a 0, and then y0 has to be a 1, and that's the only time you end up with t1 being a 1. So in that case, it's pretty obvious, right? Because x0 is 0, so that means vu x0 VU x1, sorry. So VU x1 is a 0, and then VU y1 is basically a 1. So 0 being less than 1, I don't think we have a problem with that conclusion. So that's the base case. In the induction step, for those of you who have not taken CISP310, or you took it from someone who did not explain proof by induction, it's okay. In this class, we are not concentrating on proofs, but for those of you who want to kind of like, oh, I have heard of proof by induction, I want to see what it is. So basically what we do is we make an assumption first that the theorem, which is this part over here, okay, so this part here is the theorem itself, and we say the theorem is going to work. We make the assumption that it works all the way up to when m equals to k. And then you might be saying, but how can we make this assumption? Well, that's a whole different story. You have to take CISP440 in order to understand how it works. But the idea is we make the assumption. And then, based on that assumption, we can now write down what is VU x k plus 1. In other words, if we just kind of include one more bit and look at what value that bunch of bits, k plus 1 bits in this case, is representing, that can be broken up into something from before, which is the least significant k bits, and then the additional bit, which is xk, is really just the quantity of 2 to the power of k. So that's how I can break this up into two components and break up VU y k plus 1 into two components as well. So once I have that, tk plus 1 equals to 1, if and only if, so there are only two cases where tk plus 1 can be a 1. The first one is easy, okay? The first one is the new digit, okay? The most significant digit that I'm considering in the case of m equals to k plus 1. If xk is a 0 and yk is a 1, then it is conclusive, okay? I don't really care what the less significant digits are saying. X has to be less than y, or the unsigned value of x has to be less than the unsigned value of y, because we have this little theorem that we proved earlier, okay, in the other module. So that's one that is conclusive. So the second case is, what if the new digit that we are including in this consideration, which is xk and yk, what if they turn out to be the same? They're both zeros or they're both ones. So in that case, if you want tk plus 1 to be a 1, the only chance you get is when tk itself is a 1, because the subtraction of tk from q of k can also trigger a borrow of 1, which ends up in tk plus 1. So that's the only other way. But in this case, if if tk equals to 1, then based on the induction assumption, we can now conclude that the earlier part, or the less significant digits, are of x is less than the value of the less significant digits of y. And since the new digit is the same, it's not going to contribute anything to making one larger or smaller. And as a result, we can also make the conclusion that the first or the least significant k plus 1 bit of x, when we look at the unsigned interpretation, it is going to be less than the unsigned value of the least significant k plus 1 bits of y. So that concludes the induction step. So if you look at this and go like, oh man, I have no idea what is proved by induction because I have not taken CISP310, well, kind of look at this as a preview of the future. For those of you, I'm not sure how many of you watch Star Trek: The Next Generation. It's kind of well, the polite word these days is it's kind of a classic, by today's standard, which means your parents probably watched it and not you. But there was one episode when a character called Q flung the Enterprise, the starship in the show, into a space that was occupied by the Borg as a preview of, well, guess what? These bad guys are coming to your, solar system. You better be ready. So kind of consider this as a preview of CISP 440. If you don't understand that reference, it's okay. It's not a big deal. All right. So TM in an m-bit subtraction, it is also just called the overall borrow or just borrow of a subtraction. All right, so before we move on to signed versus unsigned discussions, do we have any questions here? Remember, the proof itself is not important. The important part is we can look at the borrow flag or the overall borrow after a subtraction, and it can determine, okay, it is a 1 if and only if the minuend is less than the subtrahend, but only if you look at only if you interpret the bits as unsigned values. All right, so we got a question. Why is VUWM equation important? Well, that's just a definition. This part here is really just a definition of what it means when we have VUWM. So this is really just defining that, oh yeah, we are just looking at the least significant m bits of a bit pattern, and we want to look at the unsigned value. We want to interpret those bits as a representation of an unsigned value. So that's the only importance of VUWM, because I want to define what it is. And this, if you remember, this is actually just coming from the base conversion module. The base conversion module has something exactly like this, but it generalized to any base. So 2 it was replaced by B as a base. Right. So the big picture, the theorem is the proof of the theorem is not important, but the real important part is if you have a 4-bit subtraction, T4 is conclusive. It can tell you conclusively whether x is less than y, unsigned. So is that okay? Does everybody grasp the significance of this theorem here? It looks awful, but that's basically what it is just expressing. All right. All right. So if we drew a table, that would be bit 1, bit 0. I'm not sure about that, or I'm not sure about what that's asking, Justin. I mean, bit 1, bit 0 of what? So that's the part where I'm not sure about. Okay. All right. So if this is okay, we can always come back and talk about this, after we get to signed versus unsigned. So let's see. This is what we had earlier, and now we can get to signed versus unsigned. I found a completely different, but I think easier way to explain signed versus unsigned. So let's see if that works or not. In other words, I am throwing stuff at the wall and see whether it sticks or not. Exactly. So signed is unsigned is it's a type. It's the name of a type that you specify in C or C++ when you want to declare an integer that does not need to store negative values. In fact, an unsigned integer cannot store negative values. When you want an integer to be able to store both positive and negative values, you usually just say it's an int, which implicitly means it is signed. All right, so we're gonna get to this module. Oh, nope, this is the, wait. I'm just looking at this. This looks like the old one. Uh-oh, did I accidentally use the old one? Or I click on the wrong link. That happens too. No, I think I just clicked on the wrong one. Oh, right. Okay, never mind. If this one is obsolete as of spring 2022. Tag, you have to start reading what you typed. Gosh. There we go. This is the new stuff here. So if you read the old stuff, it is still okay. Okay, it's just a little bit more obscured in the way that I explain things. So the new way, which is this module here, is the new way of explaining the same concepts. Okay, so let's see how this goes. All right, so I'm just going to read this sentence by sentence, because it can be a little bit difficult to follow at some point. Okay, so the set of integers in math, is kind of like, it looks like a funny looking z, has an infinite number of elements. Okay, so let's just kind of pause here. Yeah, it has an infinite number of elements, because the moment you say, but Tech, I think this integer is going to be the largest integer of them all, then I'm going to ask, well, what about this plus 1? They go like, oh man, I didn't think of that. Or if you claim, okay, this value is the smallest integer, or the most negative integer, then I'm going to ask, what about that value minus 1? It is also an integer, and now it is one less than the one that you thought was the smallest, right? Or the most negative. So it doesn't work. So that means we have an infinite number of elements when you look at the set of all integers. Or if you don't know what a set is, this is just a fancy way of saying there's an infinite number of integers. However, when you store an integer in a computer, it has to have a fixed width. Now, there are some programming languages that can handle integers of a variable width. You can do that with certain programming languages, but if you want your program to run efficiently with a normal processor, you want to fix the width of your integers to whatever width your CPU is designed to handle. So we went from 8-bit processors to 16-bit processors, and then to 32-bit processors, and now we are mostly dealing with 64-bit processors. So with a fixed width, okay, so that is referring to a finite bit width, then a finite range of values can be represented. In other words, we are now limited, okay, depending on how many bits an integer has. When you store that in a computer, that will basically confine the range of values that can be represented. So based on the discussion of how values are represented in by numbers in module 0282, a base 2 number with digits 0 to n minus 1, therefore we have basically n digits, can represent values from 0 to 2 to the power of n minus 1. So I'll give you a concrete example here. If you have 4 bits, then you can represent 0 all the way up to 2 to the power of 4, which is 16 minus 1, so we have 15. So the range of values you can represent using only 4 bits is 0 to 15. And that's exactly what the next sentence talks about. So now the question is, what if you have a value outside of this range? How is that going to be represented? So that's a trick question, and that's why section 1.1 says, well, we have a tricky answer to that question. All right, so let's move on. So the tricky answer is, one way to answer that question, the former question is, which is, how do we represent 19 using 4 bits? So one way to answer that question is simply to say, nope, you cannot do that. Okay, if you want to represent a value using only 4 bits, you can only represent values from 0 all the way up to and including 15, and that's it. Okay, anything outside of this we cannot represent. So that's one way, that's a simplistic way of answering that question. The alternative way is to look at values using congruent modulo n. Okay, so I'm going to define a few terms here just so that you guys can understand what that means. Yep, that's the module. It is actually linked from here. So for those of you who, you can certainly click Omer's link in the text channel, but you can also click on this link over here. It is right below the one that is obsoleted, so it's right here. I kept clicking the obsoleted one thinking that it was the up-to-date one. Obviously, I wasn't quite reading what I typed earlier on the same day, just about 2 hours ago. Yep. All right, so we're going to talk about the notations first. So the typical notation, if you read the Wikipedia page, um, congruent modulo n is represented like this, where a is a number, b is a number, and then this equivalence or the triple equal sign, which now you guys, your newer generation, calls hamburger. So a hamburger b mod n is the same thing as what I would use in this notation, which is a hamburger n b. So the n is basically what are we modding with? Okay, it's the divisor. So neither of these two is really telling you what does it mean. Okay, what does it mean when you say a hamburger and b? Well, all that means is a can be expressed as some kind of value as an integer plus ka, which is a coefficient times n, and b can also be expressed by the same v plus kb, which can be a different coefficient times n. So the key here is we have the same v on both sides. Okay, this v and this v are the same. And obviously they have to be the same because we are talking about modulo n. So the only part that can be different is ka versus kb. So ka and kb are coefficients. They specify what is the number of n's that we are adding to v in order to end up with a value of a. So if this condition is met for some integers, ka and kb, and some integer v that is between 0 and n, so it's going from 0 up to and including n minus 1, but n cannot be v. So as long as we can express something like this, then we call a and b are being congruent modulo n. All right, so I'm going to pause here. Okay, well, wait, I'm not going to pause yet because I have to give you an example, right? So in the notation 3, hamburger 1619 is basically asking. It is not an assertion, it is a question. It is asking, are the values 3 and 9 congruent modulo 16? In other words, can 3 and 19 both be expressed as some kind of integer plus some kind of coefficient times 16? That's what it's asking. Okay, and the answer is true. Okay, the answer is yes, it is true, because if we use the value of 3 being v, then 3 itself can be expressed as 3 times 0 times 16. And some people look at this and go like, wow, you don't have to explain 0 as 0 times 16. I do, because I need to make sure that people understand the coefficient of ka is 0. 0 is perfectly okay as a coefficient. You can simply say, I don't need to have any non-zero multiples of n. That's perfectly okay. So 19, on the other hand, can be expressed as 3 times 1 times 3 plus 1 times 16. So note how the two 3's are here. Okay, in other words, they share the same v. They are different in the sense that the multiplier or the coefficient of n are different. One has 0 and the other one has 1. But as long as the two values can be expressed as using the same v plus potentially different coefficients times whatever n is, then those two values are called congruent modulo n. All right, so I'm going to pause here. Yeah, promise I'm actually pausing now. Do we have any questions about the term being congruent modulo n? The notation is a little nasty, but in other words, if you just say, if I take a value and I mod it with n, am I looking at the same result after modding with n? That's one way to look at it. All right. And Omer is also correct that we are looking into modulo math because we only have so many bits, and with only so many bits, we only have so many different bit patterns. So the question is, we are going to okay. So section 1.2 is going to tell us why it is important to introduce congruent modulo and notation at this point of time. But at this point, we are just kind of focusing on the notation. Do we and also the concept of, do we understand what is congruent modulo, and then pick some number. I think we got at least, okay, there we go. So what about 19 plus 16, 35? So 35 is not congruent modulo 16 with either 3 nor 19, because if you want to express 35, okay, so let me type it in my little notes area here, and let me get back to my editor. All right, so let's take a look at that example, 35, right? So I want to be able to express 35 as, now the v part is fixed. Okay, if you want to check whether 35 is congruent modulo 16, the v part with 3, so the 3 is going to be here. So the question is, can 35 be expressed as 3 plus some kind of k times 16, because our n is 16 in this case, and k has to be an integer. Okay, it cannot be a fraction. Because if k can be a fraction, yes, we don't have a problem with this. But since k cannot be it is a fraction. Okay, never mind. Okay, so the answer is yes. The answer is yes. K can be 2 in this case. Yep. So k can be 2. And so 35 is also, 35 and 3 are congruent modulo 16. So Chris is correct about that. So the notation is to say 35 hamburger 16 3 is true. Yep, just okay. So this is another way to look at this. I'm just gonna pop up a spreadsheet here. So there's my LibreOffice calc. There we go. All right. So using a spreadsheet, makes it very easy to see, because you can basically say, okay, I'm gonna fix a v here. So let's just say v is 3. Okay, just to use this example. And n is 16, just exactly the same as our example. So now k can be negative, can be positive, but for now we're going to look at non-negative values. So k can be 0, and then we can say, okay, let's look at the previous one plus 1. So now when we look at I did not actually give it a term here, but I can actually just write it here, which is v plus n times k times n. So that is pretty easy to figure out, because using a spreadsheet we can just refer to in this case $2 plus k is C2, and then n is $2. Yeah, I need a dollar because it's certain references cannot float with the cell itself. So now we have these two, and then I can just kind of replicate these two cells and give you all of these things. So when you look at this column here, when you look at column D, all of these are congruent modulo 16 with everything else that is also selected. So all of these are quote-unquote congruent. So is that helping? Because I think this really kind of shows, how do we get a bunch of values that are quote-unquote considered congruent modulo 16 it's really just like that. I mean, it's just, oh, okay, so we can add v to any coefficient times n in this case. So v has a constraint. So v has to be between 0 and n minus 1. So basically v is okay, I'm not sure how many of you watch Naruto. 3 is the actual Naruto. All of these are shadow clones. Okay, so if you guys are not understanding the analogy, it's okay. 3 is basically the, I guess, the most core way to describe the value. It's really just, the most core way to define the value. Okay, you need to have a picture with him and his shadow clones, or maybe I need to hover over that. Yep, there we go. Yep, so all of these are basically considered equivalent to just 3 when we perform modulo arithmetic operations. Modulo arithmetic operations basically just means, do the usual arithmetic operation and then just mod it with whatever n is. So basically, you're just following mod 16. You're using that to follow any type of operation. Can be addition, can be subtraction, and so on. You do not change n. Okay, so the key is, when you want to use the term congruent modulo blah, that blah has to be the same. So, you cannot say, oh, I'm changing changing the divisor of the modulo operation. Once you change that, then the whole thing is not the same. So all of these are considered congruent modulo 16. Now, if you change the base to something, if you change, not the base, but if you change the divisor from 16 to something else, then it won't be the same. All right. So my watch just buzzed, which means it's row taking time. And we are going to take some row here, and then we'll move on. All right, so row taking for the 10th is right here. And the word is complementary, but don't type it because I don't want people to mistype something, or it's possible that I'm the one who typed it incorrectly. So I don't want you. Oh no, I wasn't using complementary. I was using tilde. Yeah, this is something that I just did like an hour ago, and then I just forgot. So tilde is the name, is the word. There we go. And you guys have until oh, did I set the time wrong? Oh, until 25. Okay, so you still get your usual 10 minutes to do it. All right, so as you guys are doing it, I'm gonna switch back to here. And I'm just gonna be, I will be prepared to continue the discussion, because this is how we look at negative values. How do we use a fixed number of bits, okay, but this time to represent negative values? All right. So I think most people should be done with the row taking activities, and I don't see anyone complaining that it's not accepting the answer. So I think we're good. All right. So section 1.2 is basically saying, yeah, this is all kind of interesting stuff to look up when you have time, right? But why is it applicable in this class? Well, it is applicable not because 3 and 19, are both represented as 0011 in base 2, because that's basically how 3 is represented, as a 4-bit number. Congruent modulo notation helps answer a more useful question. How do we represent negative values in base 2? In other words, we don't have a sign. Okay, normally we have a sign. If you want to represent a value that is negative, you precede the value itself with a minus, and that tells other people that we are looking at a negative value. Or you can look at a unary minus symbol as a unary operator of arithmetic negation. So that's pretty easy just for human notations. But when you're working with a computer, everything is just a 0 or 1. Okay, they're all just 0 or 1s. Whether there's a voltage or whether there's a high voltage or low voltage, I should say. So everything is just true, false, 0, 1, high, low, and so on. So in that case, we don't really have a sign. Okay, we don't have a sign that we can use to say that, oh, by the way, take the arithmetic negation of the following value or expression. So we don't have an option like that. So the thing is, the coefficient here, Ka and Kb, they don't have to be non-negative. They can be negative. So that means that opens up new possibilities, because now, in this new example here, we are looking at the values 3 and negative 29. As it turns out, these two are also congruent modulo 16. Because 3, okay, we looked at 3 already. 3 is not exciting at all, because 3 is just 3 plus 0 times 16. Boring. But negative 29 is a little bit more interesting, because it is also 3 plus, and this time the multiplier or the coefficient is negative 2. Because negative 2 times 16 is negative 32. And if you add 3 to negative 32, you get negative 29. Okay, so that means, there are ways to look at the same bit pattern and say, well, this thing here can also be representing a negative value. Now, having a coefficient of negative 2 is kind of silly, because it's kind of like, going around the clock more than once. So you kind of lose track of, where you were, to begin with. But if this coefficient, if the negative 2 is actually just negative 1, then we have some possibilities. They are coefficients. These two are basically coefficients. If you want to call A and B congruent modulo n, then you have to be able to meet these requirements. You have to find Ka and Kb, and they have to be integers, and then you have to find V that is common to both of these expressions, and V has a constraint of being greater than or equal to 0 but less than n. So Ka and Kb, they need to exist in order to call A and B congruent modulo n. It's the multiplier. It specifies how many times are we going around the clock, so to speak. Okay, so we got 2 people asking questions. There we go. Oh, okay, that's an easy one. All right, so Ka and Kb, nope, Ka and Kb they're normally, when they are useful for us, they're either a 0 or a negative 1, as we will show in the table. Then the text itself is wrong. I'm not sure what you mean by the text itself is wrong. The text of what is wrong? Three and 19 are congruent modulo 16. That is correct. 3 and oh, okay, yes. Okay, I see. I mistyped here. Good job. You guys have good eyes. Thank you. So let me go ahead and fix that. Alright, so we're gonna have to store this one first, and then we'll go ahead and fix it. Yep, I prefer to fix it right away, because if I don't, you guys will be reading wrong information, so that would not be good. Alright, so I'm looking for 3 and 16, and we found it. Change it to a 9, and then we have to re-upload this module. This is 0351, I think. So PD HTML. And then refresh the power server. And now we can switch back to the notes of today. And the module should be refreshed now. So good job, you guys. Liu Zhao, you did a good job, catching my mistake. And where is that module? Right here. All right, Control Shift R to refresh, and I believe it is fixed now. Um, 4 and 19 are congruent 15. Yes, congruent modulo 15. That is correct. It's not my own server. It is the power server, which is managed by the school. But I am planning to move everything into a server that I'm quote unquote hosting. It's still a virtual server that some other company is hosting. I'm just paying for it instead of the school. The reason I'm not gonna talk about it here because that's gonna take a little bit of time. So let's go ahead and take a look at this table here. Okay, so we are looking at n being 16. V is, remember, V is quote unquote the core value that we want to represent, and it has to go from 0, including 0 itself, up to n minus 1. In this case, it's up to 15. So there are basically two values, A and B. A is okay, so A is using a 0 for the coefficient, and then B is using a -1 as a coefficient. So when Ka equals to 0, these are the values of A that we get. When Kb is a -1, these are the values that we get for B. So do we have any questions about this table? It's really just kind of spelling out the specific cases. What happens when the coefficient is a 0? What happens when the coefficient is a -1 for every single possible value of V? So I want to just kind of let you guys look at this and make sure that we understand what this table is trying to tell us. All right, I'm not seeing any questions. Shall we move on? Are we good with what this table is representing? Well, let me just kind of pick an example here. Okay, so I'm just going to pick this as an example. Okay, so pick this row here as an example. So what this row is trying to say is once we fix V equals to 7 by using 0 as the coefficient, then we end up with the value of A. On the other hand, if we make an assumption that the coefficient is -1, then we end up with the value of -9. But since they're on the same row, the A and B, the 7 and the -9, they are congruent modulo 16 in this case. So basically, if you just look at A and B of the same row, those two are congruent modulo 16. So it's really just kind of really spelling out for the two special cases when Ka is a 0 and Kb is a -1. All right. Okay, so very good. So A is the positive interpretation and B is the sort of negative interpretation. Yes. All right. So if you look at V, okay, these are the quote unquote natural way of interpreting a bit pattern. Okay, so 0, 1, 0, 0 is going to be a 4. The question is, okay, if you look at 0100 as a 4-bit pattern, um, it can be representing, not very excitingly, okay, it can be representing just 4, okay, because that's the normal way of interpreting a bit pattern. But using a -1 coefficient, the same bit pattern can also be representing -12. So now it's confusing, right? Because now we're looking at a bit pattern and go like, so which one is it? Okay, so even if we limit ourselves to say that we will either use a coefficient of 0 or a coefficient of -1, we still have two choices. We are still going like, okay, but which one are we going to choose? So here, is so I'm switching back to C++, concepts in C++. So in C++, the unsigned type uses ka equal to 0. In other words, when you declare a variable as an unsigned integer, then you're going to use only the column for a. Okay, you're not looking at any negative value. So that's what happens when you say something is unsigned. If you use the type int, which is implicitly signed, then you cannot just use kb equals to -1, because if you use kb equals to -1 and only that column, then all the values you can represent are negative. You cannot represent positive and negative value. So now we have to kind of choose a balance, right? Because I want to be able to represent some non-negative values and some negative values. So where am I going to draw the balance? You have 16 values to represent, and you have to strike a balance and say, okay, I need some negative values and I need some non-negative values. So the breakpoint turns out to be the first 8 rows. Okay, these are the first 8 rows here. They are always going to be using a equals to 0. In other words, the coefficient is 0 for these first 8-bit patterns. And then for the second 8, if you want to declare a variable as int, which is signed, then we use kb equals to -1. We use -1 as a coefficient. Okay, what happens if you try to assign a negative value to or try to decrement an unsigned integer? It basically would boil it. Okay, so underneath your C statement, it really doesn't care about the interpretation. So if you assign a -2 to an unsigned, it's going to be a huge, gigantic value because it's going to be using the interpretation of congruent modulo 2 to the power of the width of the integer. So when you assign -2 to an unsigned integer, then the unsigned integer is going to have the gigantic value that is congruent modulo 2 to the power of the width of the integer. So that's going to be let me think. It's actually going to be just 2 to the power of 32 minus 2 without the extra -1 in parentheses. Take out the -1 after 2 to the power of 32. Yep, there you go. Yep. So that's assuming you have a 32-bit wide integer. Now you can test it too. I mean, you can actually go into GDB and very quickly test whether that is the case or not. All right. So the balance point. Okay. So I'm just moving on to this paragraph here. The balance point is we use half and half, and the range. Okay. So we got some more questions here. Interesting. Yep. That's a good one. Good one. Fascinating. That's kind of what happens when an int overflows. Well, integers, this is one thing about C and C++ that's really kind of, it's bad for beginners. Now, in Visual Basic, in C#, okay, if you try to increment an integer beyond the largest value that it can represent, it would actually cause a it would cause an exception. So you can either catch the exception and process that using a catch statement, or if it is uncaught, then the program is gonna quote unquote bomb out. But when it bombs out, it does tell you that we have a problem with, oh, this, the value after this operation can no longer be represented using this type of integers. C and C++ doesn't care. Okay, if you just keep incrementing, it will wrap around on the other side. So before this, new notes here, I used to use a number wheel to represent values, and you can kind of imagine that you're just kind of going around in a circle on the wheel. All right, so let's see right here. So generally speaking, given that you have an n-bit integer, the range of unsigned is going to go from 0 to 2 to the power of n minus 1. Huh. I did not know. That problem is actually quite often. It happens quite often. Every time when people use a fixed width integer, because at the time they thought, hey, this is going to take care of all the possible values that I need to process, and then as time goes on, values got larger and larger, and then at some point, they're going to run out of values that can be represented given the width of the integer. Sort of. Okay, when you look at signed integers, it's kind of like that, because when you run out of positive values and you add one to the most positive value, it becomes the most negative value. Yep. All right, so getting back to the range of values, the range of an int, which is a signed integer, is going from -2 to the power of n minus 1 as one whole thing, to 2 to the power of n minus 1, the whole thing, minus 1. So if you just kind of plug in n equals to 4, that will tell you, given only 4 bits, what kind of value can be represented in a signed way. It's going to range from -8 to +7. Are we good so far? All right. So here's a question. Okay, at the end here, I have a little paragraph here to see if you guys have an observation, but you cannot make that observation until you look at the column of V as binary numbers. But let's talk about the observation first. Do you notice any pattern for negative values as B that are in range? Because we still have to make sure that we only talk about values that are in range, as described in the previous paragraph. Furthermore, what is a good name for bit 3 in this specific case? All right, so let's go back to here, and we can make that observation together. All right, so if you just look at all the negative values that are in range, what are those? Well, we know -1 all the way to -8. These are all in range for a 4-bit signed integer. All right, so -9 is out of range, -10 is out of range, but -8 is the most negative value that you can represent using 4 bits. So that part is okay. What we want to observe is if you look at 8, 9, 10, 11, all the way up to 15, do you notice anything that is common to all of those bit patterns? Now I can spell them out a little bit here so that you guys don't have to do the conversion. 8 is 1 followed by 3 zeros. 9 is 1 0 0 1. 10 is 1 0 1 0. 11 is 1 0 1 1. 12 is 1 1 0 0. 13 is 1 1 0 1. 14 is 1 1 1 0. And then 15 is 1 1 1 1. So do you notice a pattern? Well, They only have 4 bits. That's a given, right? Because we are talking about modulo 16, and guess what? 16 is 2 to the power of 4. So having 4 bits is is not the pattern that we are looking for. Each one is incrementing by 1, but that's only because that's how the table is listing them, right? 8, 9, 10, 11. They're incrementing. No, no. Think about the most significant bit of all of these. The most significant bit. Exactly. So Bernard is correct. Okay, bit 3 of all of these of the binary representation of all of these values, the most significant bit is a 1. MSB is a 1 with a lowercase b, please, because otherwise it becomes the most significant byte. So we use uppercase B for byte, lowercase b for bit. So it is uppercase M, uppercase S, and then lowercase b to represent most significant bit. No. Yes, John has it. John has it correct. Okay, so it's uppercase M, S, lowercase b. So yes, the most significant bit are 1 for all of these cases from 9 to 15. But when you look at the actual value that we want these bit patterns to represent, they are all negative. So does this remind you of something from the previous lab on Tuesday? And this is a hint right here. What is a good name for bit 3 in this specific case? The instruction for the questions on Tuesday introduces a term that is relevant in this case. The sign bit. Very good. All right. So I gotta give you the applause right here. Exactly. It is the sign bit. Okay. So when the sign bit, which is basically just the most significant bit, is a 1, that means if I choose to interpret the bit pattern as a signed integer, the value being represented is going to be negative. That is the significance of the sign bit. Yes, I found my little gadget thingy. Yep. Alright, so we are almost done with this entire module. So now we're going to look at arithmetic negation. In other words, how do I do something like, just taking the arithmetic negation of a value? So in normal math, it's not a big deal, right? So, but in when we're looking at base 2 representation of negative values, this turns out to be an interesting thing to do. Okay, so we'll go ahead and I just want you guys to look at this first. Negative v, whatever v is congruent modulo n with minus negative v plus k times n for some k. K just has to be an integer. Is that okay so far? I mean, this is kind of how we defined congruent modulo n, so it's kind of by definition, this is true. Are we good so far? All right, cool. So now what we do is, by the definition of congruent modulo n, that said, okay, that just explains this congruence. That said, let's consider a much more specific case when k equals to 1. In other words, we are fixing the case when the coefficient is just 1. So when we fix k equals to 1, then the whole thing, we can now say the arithmetic negation of v is congruent modulo n with the arithmetic negation of v plus n. Okay, so that really should be easy to understand. All we're doing is to say, well, this k can be any integer, but I choose to say, what if k equals to 1? over here. Okay, so that's just a very specific case of this one here. So now from here to here, it's really just to say, but I want to write n out as n minus 1 plus 1. And specifically using these, the parentheses nested in this particular way. So nobody's going to complain. Some people may have a question, but nobody's going to complain because, yeah, I suppose you can write n as n minus 1 plus 1, okay, and then put the parentheses like this. Okay, so by manipulating the positions of stuff, I can now rewrite this entire thing as n minus 1, the entire thing, minus v, and then this entire thing plus 1. Do we have any complaints here? I mean, this is algebra, right? I mean, it's I probably shorten it, by a few steps, but I think most people would look at this and go like, yeah, we kind of get it because there's a negative of v, negative of v is still here. There's a negative 1, it's still here, and then there's a positive 1, and it's still here. So all the components are here. It's just that the ordering of the operations have changed a little bit. So are we good so far? Are we getting all the way from the arithmetic negation of v is congruent modulo n with n minus 1 minus v, and then the whole thing plus 1. Are we good at this point? And then the other point that is kind of important is, even though this one here is congruent modulo n, these guys over here are equalities because they are truly equalities, just by algebra. All right, so I'm going to pause here, okay, and see if you guys have any questions about the derivation, and then after that we'll talk about why this is significant. All right, not seeing any questions. All right, all good. All right, so without any questions, so the bottom line is we have just established this. It's not an equation per se because we're not using the equal sign, but nonetheless, this is just something that is true for any type of value of v. Okay, so now we're going to say, what if n is a power of 2? What if n equals to 2 to the power of m for some integer m is greater than 0? Okay, well, it's not a big deal, right? Because all we have to do is to replace all the references of n with 2 to the power of m here. And you can see how I even changed the congruent modulo mn with congruent modulo 2 to the power of m. Yes, so there's subscript and then superscript in the subscript itself. Yep, but nonetheless, it's really just a notation thing, right? We are just replacing all the references of n with 2 to the power of m. So what we want to do now is to focus on just this part of the thing. Okay, the plus 1, we can always kind of handle that later, but we want to look at this part here. So when m equals to 4, this is a concrete example. So when m equals to 4 and v equals to 3, then we have this expression here because we are just substituting, because we say v is 3, so the arithmetic negation of 3, which is negative 3, is congruent modulo 16 with the following, which is 2 to the power of 4 minus 1, which is it becomes 15 down here, minus 3, and then the whole thing plus 1. So now we look at this sub-expression, which is 16 minus 1, the whole thing minus 3. You guys are going like, Tech, why are we talking about arithmetics in this class? Because it gets interesting. So 16 minus 1, the whole thing minus 3 is really just 15 minus 3, which is 12. So it is hardly exciting up to this point, until we look at the representation of 15 in base 2. Because 15 in base 2 is 1, 1, 1, 1 in base 2, and 3 is 1, 0, 0, 1, 1 in base 2. 3 is not the interesting part. 15 is. So as it turns out, for all m, integer m, well, not integer, but natural numbers m that are greater than 1, the binary representation of 2 to the power of m minus 1 always consists of m contiguous ones. What does that mean? Well, that means if you have m being 16, then 2 to the power of 16 minus 1 is going to be in binary. It's going to be 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1. 16 contiguous ones. All right? So that is interesting. Why is that interesting? Because if you are subtracting any type of bit pattern from all ones, then we are, so when you look at ti plus 1, this is just a reference back to the binary subtraction module. So if you know that xi is always a 1, what is the implication of this? The implication of this is if xi is always a 1, then the negation of 1 and something is always a 0. So this part here is always going to be zeroed out. Then you look at the second part. Now, the second part says, well, part of it depends on y. But what if I tell you that ti is also guaranteed to be 0? So if ti is guaranteed to be 0, I don't really care what is exclusive OR of between xi and yi. This entire term, t of I plus 1, is guaranteed to be a 0. Now, how do we prove this? Once again, it is proved by induction, but I can tell you that it's really easy to prove this one. Okay, so t of I, no matter if you look at the entire row of t, okay, after a subtraction where x is just a whole bunch of ones, you are guaranteed that there'll be no borrow of 1 whatsoever in the entire subtraction. All right. So what, right? So what that is the case. So if that is always the case, okay, then we can actually come to the conclusion that d of I, which is the different digit, is always going to be the same as q of I, and that in return is the negation of yi. And this negation of yi is not arithmetic negation. This is Boolean negation. All right? So we are doing a bitwise NOT per position of y when we subtract a bit pattern y from all ones, which is basically x in this case. So that means when we write this thing here, 2 to the power of m minus 1 minus v is really tilde v. That's why I chose the word tilde for row taking, because tilde is the symbol of bitwise NOT in C++. So that means, oh wait, hold on a second here. This is weird, right? Because the arithmetic negation of v, whatever bit pattern of v is exactly the same as the bitwise NOT of the bit pattern, which means 0 becomes 1s and 1s become 0s, plus 1. That's how we can perform the same thing, or what is equivalent to arithmetic negation is simply to say, let's do a bitwise NOT and then add 1 to the result of the bitwise NOT. All right. So we're almost done, because you kind of need this part for the lab. So do we have any questions at this point before I move on to talk about just notations at this point? The rationale is sort of important, but more importantly for the lab is how you apply what we have derived here. All right, so we got a few people typing. All right. So tilde represents bitwise NOT. How do we use bitwise NOT? Okay, I can show you some examples. And let's see. Where's my note? Right here. Okay, there we go. All right, so I am going to use C notations here. So that means if you say tilde. Okay, so in 4-bit math. Okay. because I'm not ready to use like 32-bit math. That's just a little bit too much. And I want to turn on light mode. There we go. All right, so in 4-bit math, tilde 3 is going to be tilde, let's see, 0011 in base 2. And that means you just basically flip all the zeros to ones and flip all the ones to zeros. So you have 1100 in base 2. Are we doing okay so far with this? That's bitwise not. Now bitwise not, has a lot of other applications, but in the context of what we are talking about here, that's basically all we need to know is it just flips, zeros and ones. All right, cool. All right, so next, what do we do? So we are basically just using a different notation, one's complement. So tilde x, which is bitwise not of x, is also called the one's complement of x. That's just a term. Okay, it's nothing more than just a different name for the same operation. Okay, bitwise not of a bit pattern is also called one's complement, which I use C1 here to represent, of the same bit pattern. So this part is just name. Okay, nothing really significant other than the name. So C2, on the other hand, or 2's complement of x, is defined to be 1's complement of x, x being a bit pattern, plus 1. And that turns out to be the same thing. It's equivalent to taking the arithmetic negation of a bit pattern. Are we doing okay so far? So there's an example down here. So the question is, how is the arithmetic negation of 3, which is -3, how is it represented as a signed 4-bit integer? So as a 4-bit integer, we know that m equals to 4 in this case. So what we do is we start with 3. 3 itself has a bit pattern of 0, 0, 1, 1. And then we plug 3 into the place of x up here. Okay, so this x here, we plug 3 into that space because we're trying to do a negation of 3, arithmetic negation of 3. So now we have C2, or 2's complement, of 0, 0, 1, 1 because x is 0, 0, 1, 1. But 2's complement is really 1's complement plus 1. So now we say 1's complement of 0, 0, 1, 1 is 1, 1, 0, 0. And then you add 1 to 1, 1, 0, 0, you end up with 1, 1, 0, 1. So are we okay? Are we okay with this example here? Now, one thing we might want to check is in the table that we had earlier, if we look at a column where the coefficient is -1, do we find -3 for this specific value of v? Now this particular value is actually 13, so we want to see if when v equals to 13 and the coefficient is -1, are we seeing b having a value of -3? So going back to this table, when v equals to 13, which is really just looking at the bit pattern of 1, 1, 0, 1, when the coefficient is a -1, we do indeed see the value of b being -3. So it is very consistent with what we talked about earlier. And then there's a question in the text channel. Are the smaller numbers 2 is the number subscript just to telling us that it is in base 2? Yes, that is a notation that we use to denote what base we are talking about. And that's it. I mean, this is this is the last one. So if we perform a double arithmetic negation, we should get the original value back, right? So what is the arithmetic negation of the arithmetic negation of 3? So now we use the congruent symbol here. And we are looking at because whenever we take arithmetic negation, we can use 2's complement to do the job. So now we are saying, okay, what is -3? -3 we found earlier has a bit pattern of 1, 1, 0, 1. So now we are really just taking the 2's complement of 1101, because taking the 2's complement of something is the same thing as the arithmetic negation of something. 2's complement expands to 1's complement plus 1. 1's complement is really just flipping all the bits. So if the original bit pattern is 1101, then it becomes 0010, because all the 1's become 0s and all the 0s become 1s. So now we have 0010 plus 1, which is 0011, which indeed is 3. So that concludes, that concludes everything that you need to know for tonight's lab. So the application of 2's complement is what you need to use for the lab tonight. Everything else are just rationale leading to this part. Alright, so while you guys are asking questions, I am going to open up the lab. So the lab is called 2's complement, and I'm gonna unlock it now so you guys can see it. Alright, so I'm going back to the text channel. So is the major takeaway here to show us how we can get to 2's complement to show different interpretation of a bit pattern? Yes. You can call it the scenic route of explaining 2's complement, and also how signed values are represented using a fixed width bit pattern. I'm just trying to figure out why we went through the discussion. So those are all rationales. Okay, so basically, now we have the tool that we need in order to actually implement 2's complement. Okay, because 2's complement is really important when we want to know what value is being represented by a bit pattern. But I don't like just to explain to you, okay, just use this tool, press this button and this will happen. I want to explain to you how the tool itself operates. And that's basically the majority of the time of today's lecture, is basically taking apart an electric drill to show you what is inside an electric drill. And then at the end of the lecture, I put the whole thing back together and then go like, vroom, vroom. This is how you use it, okay? You'll just put a drill bit on it, and now you can start to drill stuff. Versus the discussion you had about the number wheel in the older notes, which seem a little more intuitive. That one is intuitive, but it's not mathematical. Okay, that's kind of the best way I can put it. Intuitive stuff is good. However, they can be wrong. Something can be intuitive but not actually right. So what I have right now, the replacement module. So instead of using the original module, this new module is a lot more rigid when you look at it from the mathematics perspective. All right. So Chris said back to the initial example of 3 is 19 mod 16. So negative 19 would be negative 3 mod 16. Yes, that's one way to look at it, but negative 3 itself is 13. I mean, negative 3 and 13 are congruent modulo 16. Can we use the notion of 2's complement for binary subtraction? Yes. Okay, so let me just kind of show you the math here. I can give you guys more time for tonight's lab, which is not what you want to hear. But I want to kind of comment on Igor's observation, because that is a very good observation. Alright, so I'm just going to explain it here, and you guys can actually try this out in the C program. So in a C program, so I can just kind of append to this one. So in a C program, we have integer x and we have integer y. Okay, so if you look at the expression x minus y, it really gives you the same value when you say this is the same thing as x plus, and then you perform the arithmetic negation, but not using arithmetic negation. Instead, you basically say, oh, arithmetic negation is really the same thing as bitwise not of y plus 1. So this equality here should always hold, because when you subtract y from x, you are basically adding the arithmetic negated version of y to x, but we know that the arithmetic negation can also be done using bitwise not plus 1. So you can try this out. I mean, you can really just write a very simplistic C++ program, declare two signed integers x and y, give them initialize those two variables to certain values, and then you can just look at, okay, what is the value of this expression, and then you can look at what is the value of that expression. They should be identical for all possible values of x and y. So yes, so Igor's observation is correct. You can actually just use 2's complement plus 1 to handle subtraction. All right, so we are a little bit out of time. It's 7:03. You have the usual 3 hours, so I'm gonna push back the due date by 13 minutes. So it's due at 10:03. I don't think it's gonna take you guys that long. Okay, I'm just doing it because, yeah, just because. All right, so unless you guys have questions, if I don't see any questions in the text channel, I'm gonna stop the streaming. But I want to record this first, just so that people know that I have postponed the due date or the time just a little bit. So it's 10:03 p.m. 10:03 p.m. There we go. So now you got 13 minutes more to get the lab done. All right, I am not seeing any new text messages, so that means I am going to stop streaming. I will go away, have some snack, and